to Chantier Proof. Next talk is by Andy's on another matrix multiplication extension proposal. And with that, over to the speaker.
Hello, everyone. Thank you for being here. I'm Pei-Hsiang from Andy's Technology. Today, I would like to talk about accelerating AI models with Andy's matrix multiplication, or AMM for short. We'll see how AMM helps optimize convolutional neural networks and large language models. Not much that I do. It's not my slide. Okay, so here's the outline. First, I will introduce Andy's matrix multiplication and illustrate its scalability. Next, we will look at the AMM code generation using the I-WEI framework, especially for the large language model deployment. Finally, I will share some performance assessments showing how fast AMM might be. So AMM is being designed to optimize tiled matrix multiplication. Look at the diagram. We break down the large matrices into the smaller tiles. So AMM performs matrix multiplication on a name by k tile from the matrix A and k by n tile from the matrix B. Then we produce a name by n tile in the matrix C. Moreover, AMM has several key features. First, these small tiles are stored in the I-WEI vector registers. No extra matrix registers or accumulators are needed. Next, AMM offers 2D load and store instructions to facilitate the tile movement from memory and between memory and the vector registers. Next, AMM is scalable across different VLEN settings, like VLEN, SEW, and LMO. So to help you understand the tile size, here's a quick summary. First, M is always 2, and N equals VLEN divided by 64. Next, K is determined by LMO and SEW. So now let's zoom in on scalability. Here's VLEN scalability. Okay, so VLEN is the vector length, which depends on specific VPU implementation. And since AMM reuses the I-WEI vector registers, it's crucial for AMM to be VLEN scalable. So look at the illustrations here. Assume that we are multiplying F32 data type and NORML 1. So as you can see, the dimension M is always 2, and the dimension K is 2 as well, since we have F32 data type and NORML 1. The only thing that changes with VLEN is the dimension N. When VLEN doubles, N also doubles. LMO scalability. LMO is the vector length multiplier, which allows us to group multiple vector registers together to act as a single longer vector register. AMM supports the integer LMO values, but not the fractional LMO values, because AMM handles those situations using boundary control, which I will explain later. So consider F32 again, and VLEN 128. This time, the only thing that changes with LMO is the dimension K. When LMO doubles, K also doubles. So this design allows AMM to process more data in parallel along the dimension k. SEW is the size of data type. AMN will not only support various data types, but also data widening, like 4x widening from int A to int 32, or 2x widening from F16 to F32. So let's consider VLEN-128 and Elmo-1 again. This time, the only thing that changes with SEW is also the dimension k. When SEW doubles, k is halved. So to support this tiled approach, efficiently moving the tiles between memory and the vector registers is crucial to performance. So AMM offers 2D load instructions to transfer the tiles from memory into the vector registers. Notably, they can transfer the KN tiles, typically the weight matrix, in either row major or column major order. And it's helpful when the weight matrix is not stored in a transposed data layout. On the other hand, 2D store instructions write the resulting tiles back into memory. So boundary control. When the imp shapes are not exact multiples of the AMM tile size, we set a spatial control and status register to tell the hardware how many elements are active. So consider this example here. The dimensions k and n are not multiples of 2. So first, we compute the major part of the matrix in blue color using standard AMM. Then, for the edges of the matrix in yellow color, we use AMM with boundary control to load, compute, and store the active elements while ignoring the inactive ones. So no extra software padding is needed. So let's talk about the software stack for AMM. We have integrated the AMM code generation into the I-WEI framework and leveraged the open source tool Shark AI to build AI models in PyTorch and add KV cache optimization. Then we use I-WEI Turbine, I-WEI's front end for PyTorch to compile the models into the high-level torch direct. And then the I-WEI compiler lowers the high-level torch direct into the linear algebra direct. At this point, we identify the matrix multiplication patterns and convert them into our AMN dialect. Finally, AMN dialect is further translated into LLVM to generate machine code for ND's cores. So now let's see how our core generation path selects the best tile size, generates VLEN-agnostic code, and handles the 2 stages of LLM. To determine the best tile size at the register level for AMN, the compiler needs to decide on the Elmo values, which limits the number of vector registers available, and the unrolling vectors of the tiles. So by setting the Elmo values to 4, unrolling the KN tile by 2, and the MK tile by 8, the compiler arrives at a register level tile size of m equals 16, n equals 16, and the k equals 8. This best tile size completes the most operations while having the lowest execution latency. So the problem of the previous fixed tile size is it's only suitable for VLEN 512, not for VLEN scalable. So what we do is to express the dimension n as 2 in the square bracket, which means 2 times V-scale in I-WEI. And V-scale is a runtime constant provided by hardware. Specifically, V-scale equals VLEN divided by 64. So now you can compile your AI models just once and scale performance across VPUs with different VLEN configurations. So let's examine the two stages of LLM. The first one is the prefill stage, which initializes the model with user prompt, and its dimension M is dynamic and depends on the size of token sequence. So what we do, in our approach, we generate two kernels to handle the dynamic shape. The primary one is the AMM kernel, which performs most of computations. And the second is the RISC-V kernel, which handles the remaining rows when M is not a multiple of 16. So the next is the decode stage, which features a GEMV operation. So for this specific scenario, we choose to generate optimized RISC-V code because it's more efficient than AMM in this case. So performance comparison, AMM versus RISC-V. We have evaluated the two models, MobileNet V1 with int8 to int32 computation, and the TinyLlama 1.1b with 8-bit quantization where the weights are dequantized back to F32 at runtime. For the hardware configurations, both AMM and RISC-V have a VLEN of 512, but AMM has 8 times more max than RISC-V. So the table shows the AMM performance speed-up estimates over RISC-V. For the GMM operator, the speed-up is 6.4x and reaches a strong 80% AMM max efficiency, showing the computational advantage of AMM. For the MobileNet V1 and TinyLlama prefill stage, the speed-ups are 2.7x and 2x respectively, and AMM max efficiency drops to 34% and 25% because GMM operation only takes up 75% and 60% of the model's execution time. So conclusion, we have seen how AMM is being designed to optimize tiled matrix multiplication. Moreover, we have integrated the AMM code generation with I-WEI to optimize AI models without requiring any programming or optimization efforts. Finally, AMM shows significant speed up for GEMM operation. As for the full model, we will continue optimizing the nonlinear operations to make the speed up of AMM more apparent. That's all I have for today. Thank you.
Thank you very much. And we'll be skipping questions again. Please feel free to find the speaker later. So we're heading